Come on, my dears. Now kindly read this statement of illustrative numerical number 7. Read it. Come on. We are given 2 point charges. First point charge is, say, Q1, which is 10 raised to minus 9 coulomb, and because it is located at origin, its position vector is vector R1, which is 0, 0, 0. Many times, just for sake of our convenience, we represent position vector in terms of its components, and which are nothing but coordinates of a given point. Okay, fine. For origin, all the 3 coordinates are 0, 0, 0, correct? Second point charge is capital Q, which is located at a position whose coordinates are given in the statement 2, 0, 0, that many meter. Okay, fine. Now, a point where we find electric field is called point of observation, and for that point in the statement they have given these coordinates 3, 1, meter. Okay. Now, we are asked to find out the value of charge Q such that the resultant electric field at this very point should have its x component 0, correct? First of all, let us recall the expression for resultant electric field made produced out of an electric charge system made up of, say, n number of point charges. In the theoretical part of this chapter, I had derived this formula, and that formula was vector E as a function of vector R is equal to k into sigma from j is equal to 1 to n. What was n? Last order of the charge. Last order of the charge. Here we are given only 2 source charges. How many source charges? 2 source charges. The charge which is responsible for producing electric field, which becomes source of electric field, is called source charge. We are given 2 source charges, that is why I am writing j is equal to 1 to 2. Suppose we are given 3, then you may write j is equal to 1 to 3. Right now 2, so j is equal to 1 to 2. Then into qj upon mod of vector r minus vector rj whole cube into vector r minus vector rj. Got it? Fine. Now, just place j is equal to 1, and then after just place j is equal to 2, that is all. This small k as it is. First of all, place j equal to 1 here everywhere. Come on, when you write j equal to 1, it will appear now q1 into vector r minus vector r1 upon mod of vector r minus vector r1 whole cube, and because it is sigma, I must write plus sign, and after j equal to 1, you may write j equal to 2. Come on, write everywhere j equal to 2. Then it will appear q2 into bracket vector r minus vector r2 divided by vector r minus vector r2, its mod and its cube. Mod of vector r minus vector r2 whole cube, correct? Fine. Now tell me, here we require not only vector r minus vector r1, we require its mod also. Similarly, we require vector r minus vector r2 and its mod also. So let us try to find out those values. We know vector r, we know vector r1, so definitely we can find out vector r minus vector r1. Vector r minus vector r1, this minus this, so now it is 3 minus 0, that is 3. 1 minus 0, that is 1. 1 minus 0, that is 1. Correct? That many meter. Now I want modulus of this vector. Modulus of any vector means square root of summation of squares of its three mutually perpendicular components. Come on, three mutually perpendicular components are right now 3, 1, 1. And then how will you find out modulus of this vector? Come on, mod of this vector will be under root of square of this plus square of this plus square of this, correct? Square of 3 is 9, square of 1 is 1, square of 1 is 1. Now this addition is 11, and because it is square root, the power should be expressed as 1 by 2, 11 raised to 1 by 2, correct? Now let us try to find out vector r minus vector r2. Vector r minus vector r2, it is this minus this. Now 3 minus 2, that is 1, 1 minus 0, that is 1, 1 minus 0, that is 1, correct? Take now modulus. Modulus of this means square root of summation of squares of this, and this, okay? Come on, square root of summation of square of 1 is 1, square of 1 is 1, square of 1 is 1, okay? Inside addition is 3, its square root means 3 raised to 1 by 2, okay? Now let us place all these values in this step now. Come on, don't you know value of small k, proportionality constant coming in Coulomb's law? Remember this value, 9 into 10 raised to 9 Newton meter square upon Coulomb square. Q1 is the first charge given to us, 10 raised to minus 9 Coulomb. You must write in Coulomb only, in SI unit only. If it is given to you, suppose in micro Coulomb, you must multiply by 10 raised to minus 6, you must convert it into Coulomb. Got it? Fine. Now what about vector r minus vector r1? Vector r minus vector r1 is 3, 1, 1, 3, 1, 1, divided by cube of this modulus. Come on, cube of this will be cube of this. When you take cube on both the sides, now here when you take cube, 11 raised to 1 by 2 whole raised to 3, that is 11 raised to 3 by 2, 11 raised to 3 by 2. I am writing here 11 raised to 3 by 2, correct? Plus, what about Q2? Q2 is capital Q. Q2 is capital Q. What about vector r minus vector r2? Vector r minus vector r2 is 1, 1, 1, 1, 1, 1, divided by cube of its modulus. Come on, vector r minus vector r2, its modulus is this. Now its a cube means cube of this. When you take cube of this, it is 3 raised to 1 by 2 whole raised to 3. Again it is 3 raised to 3 by 2, 3 raised to 3 by 2, 3 raised to 3 by 2, correct? Now here their requirement is to make x component of resultant electric field to be 0, and for that sake what should be value of capital Q? That is what we have to find out. So we should now go for finding x component of resultant electric field. That's why I am putting the symbol EX. You must write this x as a suffix well below the symbol capital E, okay? Now when you want to have x component of this vector, this multiplier you should retain as it is. Come on, this is kept as it is, this multiplier 10 raised to minus 9 as it is, but wherever there is a vectorial form having x, y, z components, among 3 components you are interested in finding out only x component. So take only x component, which is 3, multiply by 3, this part as it is. Come on, plus this multiplier capital Q as it is. Among these 3 components we want only x component, which is 1, so just multiply by 1 divided by this part as it is, okay? But what is their demand? Their demand is to have x component of resultant electric field to be 0. So equate this value with a 0, okay? Because x component of resultant electric field they want 0, correct? Now simplify, bring this down, okay? 0 upon anything will be 0. So this whole bracket is 0, and now just make this part as subject of the equation. So you may transfer this part on right hand side, from plus it will become minus 3 into 10 raised to minus 9 and divided by 11 raised to 3 by 2. But I want capital Q, so transfer this part on the right hand side in the numerator. Come on, Q equals to minus 3 as it is. When this will go up, 3 raised to 3 by 2 divided by 11 raised to 3 by 2. Both the values have power same, 3 by 2. So you can take power common. So 3 upon 11 whole raised to 3 by 2. 3 upon 11 whole raised to 3 by 2. Multiply by 10 raised to minus 9. Okay. Now, how would you find out this value using simple calculator? Very simple. First of all, you find out 3 upon 11, that is 3 divided by 11 you can find out using simple calculator, and then its a square root you may find out, square root, okay, and it's a cube, x into x into x will give you x cube, like that you can find out it's a cube, correct. And once you know this value, you may multiply by 3, that value comes out to be 0.4273, okay. This minus sign as it is, and this 10 raised to minus 9 also in multiplication as it is, okay. That many coulomb, because rest of the values we have placed in SI unit. So, naturally final answer of electric charge value will come out in coulomb. If they ask this value in nano coulomb, remember nano, deci, centi, milli, micro, nano, pico, femto, atto, zepto, yocto, correct. In that this nano means 10 raised to minus 9. So, wherever it is 10 raised to minus 9 coulomb, you can write 1 nano coulomb. So, at that time minus 0.4273, that many nano coulomb. But they have not asked the value of charge right now in nano coulomb, simply they have asked the value of charge. So, you may retain SI unit coulomb as it is, okay, fine. So, this is the final answer, okay. The way they have asked x component to be 0, they may ask y component to be 0, they may ask z component to be 0, correct, but the method will remain same, okay, fine. Now, read sum number 8, illustration number 8. Read it? Come on. My dears, here we will make use of one generalized result. What is that generalized result? I am showing you. If you have regular polygon, and then if you are placing identical point charges at all its vertices, then resultant electric field at the centroid of that polygon is found to be 0. I repeat, when we place identical point charges at all the vertices of a regular polygon, then the resultant electric field at its centroid is found to be 0. We are going to make use of this result in this sum, okay, fine. At present we are given regular pentagon. It is A, B, C, D, E, correct. They have given 4 identical point charges, each of them is small q, which are to be placed at 4 vertices A, B, C and D. That is what I have shown here, A, B, C and D, Q, 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 correct. Now, they have asked resultant electric field at this centroid O. How to find that? I am showing you. 4 point charges they have given, correct. Let us add one more point charge at the 5th vertex from our side, okay. The way in certain schemes, if you are investing some amount, then government is giving you subsidy, correct. Similarly, here they are giving 4 point charges, we are just adding one from our side. Suppose we place identical point charge here also, suppose, then just use that result just now I told you. When you have identical point charges placed at all the vertices of a regular polygon, then resultant electric field at the centroid will be 0. Resultant means vector addition of all the 5 electric fields, because there are 5 point charges. Come on, let it be vector EA plus vector EB plus vector EC plus vector ED plus vector EE. This will give you resultant electric field, which should be 0. That is 0 vector, okay. What do you mean by vector EA? It is electric field due to point charge placed at point A. Similarly, this is due to point charge placed at B, placed at C, placed at D, placed at E. Got it? But now, this first 4 electric fields will produce resultant electric field, suppose vector E dash. The resultant of these first 4 electric fields is suppose vector E dash, and this term I have kept as it is, 0 vector also as it is. Okay. What is vector E dash? Resultant electric field at the centroid of this regular pentagon because of 4 given point charges placed at vertices A, B, C and D. Okay, fine. Now we are interested in finding out this electric field. So just make subject of equation. Come on, transfer this. Transfer this. From plus it will become minus. Now tell me, what does this negative sign indicate? It indicates that direction of this is just opposite to direction of this. Fine. What about magnitude? Take modulus on both the sides. When you take magnitude here, it is E dash. When you take magnitude here, it is EE. Correct? But what do you mean by EE? EE means what? Magnitude of electric field produced due to a point charge placed at point E. Come on, place at point E. Again, it is also small q only. And for a point charge, don't you know magnitude of its electric field in words? K into charge upon distance square. K into charge upon distance square. K into charge upon distance square. Distance of each vertex from the centroid is same, which they have given in the statement as small a. Okay. So K into charge upon distance square. Correct. So magnitude of required electric field, which is E dash, is right now KQ upon A square. But what about direction? Just now I told direction of this is opposite to this. What about direction of electric field produced due to this positive point charge? For a positive charge, don't you know, electric field is away from it, away from this means from E to O, from E to O. But direction of this is opposite to that, opposite to E to O, opposite to E to O, that will be from O to E, from O to E. That's why I am writing here from O to E. Correct? I repeat. This is the electric field produced due to positive point charge placed at point E. And because of positive charge, where is the direction of electric field? Away from it, this way. Correct? That is from E to O. But that is direction of this. But we want direction of this, which is opposite to that. Opposite to E to O will be from O to E. That's why I am writing from O to E. Got it? Fine. Read now illustration number 9. Read it? Come on. We are given a square ABCD having side length small a. We are also given 4 point charges Q, Q, minus Q, minus Q, which are placed respectively at vertices A, B, C and D. You can just check it. Q, Q, minus Q, minus Q. Okay. They have asked what is the resultant electric field at the centroid O. Right? That is what we have to find out. Let us find out. First of all, you can see in the diagram, because it is a square, the distance of each vertex from the centroid is same. Distance AO is equal to distance BO is equal to distance CO is equal to distance DO, and each of them I am showing by symbol small r. Okay. Now don't you know, the diagonals of a square always intersect at right angle. That's why this angle is right angle. And if this is right angle, opposite to right angle, this must be hypotenuse. And when it is hypotenuse, you are talking about right angle triangle, you can apply Pythagoras theorem. So square of hypotenuse will be equal to summation of squares of remaining 2 perpendicular sides. So square of this that is a square, will be equal to square of this plus square of this. So it is r square plus r square. Got it? R square plus r square, that is 2r square. Find out r square, transfer this 2 in the denominator, a square upon 2. Take square root now, square root of this is r, square root of this is a by root 2. Okay, fine. Now, so far magnitudes of electric fields produced by these 4 point charges are concerned at the centroid. Those magnitudes are equal because the magnitude of charge is same everywhere and this distance is also everywhere same. That's why all these electric fields have same magnitude. EA equals to EB equals to EC equals to ED, meaning thereby magnitudes of electric fields produced by point charges placed at point A, B, C and D are equal and their common equal magnitude I am showing by symbol capital E. And don't you know formula for magnitude of electric field produced by a point charge? Don't you know? K into charge upon distance square. K into charge, magnitude of charge is Q, distance square, that is r square, correct? Come on, KQ as it is, but what about r square? R square is a square by 2, r square is a square by 2, r square is a square upon 2, denominator will become numerator, correct? Fine. Now, find out direction of electric field produced by this point charge at this very point. Because it is a positive charge, then direction of electric field is away from it, away from this, like this. That is vector EA. And what about direction of electric field produced by this negative point charge? For a negative charge, electric field is always pointing towards it. So towards this negative charge, like this. So vector EC is in the same direction. Now these two vectors are in the same direction, correct? And their resultant electric field I just show it by symbol vector E1, okay? Because these two are in the same directions, don't you know, whenever vectors are in the same direction, you can add them like scalars, okay? So magnitude of this, straight away you can write E1, which is magnitude of this plus magnitude of this. Come on, EA equals to EC equal to E. So this is also having magnitude E, this also has magnitude E, E plus E, that is 2E. Why you are making the scalar addition of their magnitudes? Because these vectors are in the same direction, that's why. What about electric field produced at point O due to this positive point charge? Come on, for a positive charge, electric field is away from it, this way, that is vector EB. Because of this negative point charge, electric field is towards it. So vector ED is towards it, towards this point, correct? Now you can see in the diagram, these two vectors are having same direction and their resultant vector I am showing by symbol vector E2, okay? Because these two vectors are in the same direction, you can add them like scalars. Then magnitude of this I am taking E2 and magnitudes EB and ED, magnitudes EB and ED, they have same value E. So this has magnitude E, this also has magnitude E, E plus E, that is 2E, correct? Fine. Now this resultant vector is vector E1, which I am showing here. This resultant vector is vector E2, which I am showing here, correct? Vector E2. Now this is vector E1, or you may say this vector. So this is vector E1, or this also is vector E1. This total vector is vector E1, this total vector is vector E2. And now you want resultant electric field at point O. It will be this vector plus this vector. Vector E1 plus vector E2. Vector E1 plus vector E2, it is vector EO. Let me write here in the diagram. Come on. Vector E1 plus vector E2 is vector EO. So vector EO is vector E1 plus vector E2. Come on. Now what about these two directions? Come on. This is vector E1, this or this, okay? This is vector E1 and this is vector E2. Both of them are at right angles. So opposite to this right angle will be this side or this vector. it is opposite to right angle means what? Hypotenuse. And when it is hypotenuse, then you can apply Pythagoras theorem. Come on, square of hypotenuse, that is EO square, will be equal to E1 square plus E2 square. E1 square plus E2 square, correct? Come on, what is E1 value? 2E. So E1 square will be, come on, 4E square, 4E square plus E2 square. E2 square, come on, square of this will be again 4E square. 4E square plus 4E square, that is 8E square, okay? Now, what about EO? I want square root of this, that is EO. When you take square root here, you must take square root here. Square root of 8 is 2 root 2. Square root of E square is E. Wait, 2 root 2 as it is. What about E? Value of E is, come on, 2kq upon A square. 2kq upon A square. And now, 2 2s are 4 root 2 kq upon A square. 4 root 2 kq upon A square, correct? This is the magnitude of resultant electric field at point O. What about its direction? Direction of this, you can see this vector plus this vector is going to give you this vector, which is direction of vector EO. And it is very much parallel to vector BC or vector AD. Come on, parallel to vector BC or parallel to vector AD. I have written here in bracket parallel to vector AD or vector BC. Okay, fine. Now, can you read the statement of illustration number 10? Read it? Come on. We are given a pair of parallel metallic plates which are unlikely charged, having perpendicular separation small d. Okay? In figure A, lower plate is positively charged, upper plate is negatively charged. And have you remembered direction of electric field? It is always from positive to negative. That is right now from lower plate to upper plate, from positive to negative, this way. So, this is the upward direction of electric field, fine. Now, in that electric field, what we release one electron from this upper plate. Now, electron has negative charge, and don't you know, on a negative charge, electric force is always opposite to direction of electric field. Direction of electric field is vertically upwards. So, now electric force will be exerted vertically downwards. That is why this electron will be accelerated vertically downwards. And just to travel this much distance in downward direction, what time is taken by this electron? That is what we have to find out. Okay? Now, in the second figure, they have kept the same magnitude of electric field, but the direction of electric field they have reversed. Now, you can check, upper plate has become positively charged, lower plate has become negatively charged. Where is the direction of electric field? From positive to negative. That is why right now it is vertically downwards. But now in this case, they have released one proton from the upper plate. Come on, proton has positive charge. For a positive charge, electric force is always in the direction of electric field. Direction of electric field is vertically downwards. So, direction of electric force is also vertically downwards, correct? So, this proton will be also accelerated vertically downwards, and by the time it travels this much distance in downward direction, what time is taken by this proton, that is also we have to find out. Okay? Let us find out both the times. Okay? Look, electric force is, come on, magnitude of charge multiplied by magnitude of electric field will give you magnitude of electric force. Electric force is always charge into electric field, and force is also mass into acceleration, mass into acceleration. Find out A from here, transfer this m in the denominator. So, Q into E upon m, give it equation number 1, fine. Now, recall from 11th standard, second equation of linear motion with constant linear acceleration. What was that? D equals to V0t plus 1 by 2 AT square. D equals to V0t plus 1 by 2 AT square. But both these particles are released from state of rest. That's why their initial velocities are 0. Put V0 equal to 0 here. So this part will be 0. 1 by 2 as it is. What about A? A is right now, come on, Q into E upon M. Value of A is, come on, Q into E upon M into T square. Just make subject of the equation T square. Come on, find out T square. 2 into M, you can transfer here. 2md divided by Q into E. 2md divided by Q into E, but this is T square. I want only T, then I want only T, not coffee, only T. Come on, take square root of this, that is T, and square root of this will be under root 2md upon QE, correct? Wait. Now use this formula 2 times, once for electron, second time we will use it for proton. First of all for electron, so instead of T I am putting the symbol TE, time taken by electron. Under root of 2 as it is, instead of M I am putting ME, that is mass of electron. Distance D is same for both the particles, okay. So D is same and constant, and divided by Q, that is magnitude of charge of electron, which is small e, and this is given electric field, okay, fine. Now 2 as it is. What about mass of electron? 9.1 into 10 raised to minus 31 kilogram into D. This separation they have given 1.5 centimeter. Converted into meter, 1.5 divided by 100, that is 0.015 meter, divided by magnitude of charge of electron 1.6 into 10 to minus 19 coulomb. What about magnitude of given uniform electric field? They have given in the statement 2 into 10 raised to 4 Newton upon coulomb. Whether you write Newton upon coulomb or volt upon meter, one and same, okay, fine. Now find out, the value comes out to be 2.92 into 10 raised to minus 9 second, okay. Now this 10 raised to minus 9 second can be replaced by nanosecond. Remember nano means 10 raised to minus 9. Deci, centi, milli, micro, nano, pico, femto, atto, zepto, yocto. In that nano means 10 raised to minus 9, okay, fine. So this is 2.92 nanosecond. Let us find out similar time for proton. Come on, instead of T I am putting Tp, that is time taken by proton. Come on, here under root of 2 into M, instead of M I am writing MP, mass of proton. D is constant. Come on, this is magnitude of charge of proton, which is small e, and this is given electric field, okay, fine. Now under root of 2 into, what about MP, mass of proton, they have given in the statement 1.7 into 10 raised to minus 27 kilogram. What about distance D? Come on, still the distance between these two plates is same as this. Come on, it was 1.5 centimeter divided by 100, 0.015 meter. Come on, charge of proton 1.6 into 10 raised to minus 19 coulomb. What about magnitude of given uniform electric field? They have given 2 into 10 raised to 4 Newton upon coulomb. 2 into 10 raised to 4 Newton upon coulomb, correct? Simplify, answer is 1.26 into 10 raised to minus 7 second. Do one thing, you just multiply here by 10 raised to 2 and here you multiply by 10 raised to minus 2. Will do na? 10 raised to 2 into 10 raised to minus 2 will make 1, okay? So here you multiply 10 raised to plus 2, here you multiply 10 raised to minus 2. When you multiply here by 10 raised to plus 2, it will be 126. When you multiply 10 raised to minus 2 here, it will be 10 raised to minus 9, that many second. But 10 raised to minus 9 second is nothing but 1 nanosecond. So this is 126 nanosecond. What was the time taken by electron? Just 2.92 nanosecond. And compared to that time taken by proton is very large, 126 nanosecond. Why time taken for traveling same distance in the same electric field? Why time taken by proton is so very large? Very simple reason is there. Look at this formula. Right now D is constant, Q is constant, E is constant. So you can think of relation between T and M, and it is T proportional to under root M. What does it mean? For heavier particle, mass is greater, and then time taken by that particle also will be greater. Compared to electron, proton is very heavy, That's why its mass is very large as compared to mass of electron. That's why time taken by proton to travel same distance vertically downwards in same electric field is very large. Okay. My dears, here in textbook they have not mentioned one point which you might click in your mind. Here in the whole discussion we have not considered gravitational force. We have not considered the role of gravitational acceleration. Why? What is the reason for that? I am showing you. Look, if you want to find out acceleration of electron, you may find it from here. At that time you can write here mass of electron, charge of electron, and given electric field value you can write here. Find out this acceleration. It comes out to be, for electron, this acceleration comes out to be of the order of 10 raised to 15 meter per second square, 10 raised to 15 meter per second square, very large. And for proton, you may write here mass of proton, correct? These two value remain same. At that time, that acceleration you will get of the order of 10 raised to 12 meter per second square. Whether it is 10 raised to 12 or 10 raised to 15, these values are very large as compared to the value of gravitational acceleration, which is simply 9.8 meter per second square. So compared to 10 raised to 12 and 10 raised to 15, 9.8 value is negligibly small. That's why we have not considered any effect of gravitational force, and hence we have not encountered the gravitational acceleration. Okay, fine. Now, kindly read this statement of illustration number 11. Read it. This sum is very easy. Have you studied in theoretical part? Whenever you place electric dipole in a uniform electric field at angle theta, then torque exerted on the dipole is given by formula. Come on, tau equals to P E sin theta. Remember the vector relation? Vector tau equals to vector P cross vector E. And when you take magnitude, tau equals to P E sin theta. What about P? It is electric dipole moment given to you in the statement 4 into 10 raised to minus 9 coulomb into meter, capital C small m, coulomb into meter. What about capital E? Electric field 5 into 10 raised to 4 Newton upon coulomb. Theta is angle between vector P and vector E, which they have given 30 degree. Now simplify. Sin 30 degree is 1 by 2. 5 4s are 20, 20 upon 2 that is 10, 10 that is 10 raised to 1, 1 plus 4 is 5, 5 minus 9 is minus 4, correct? And unit of torque you must write in SI unit, that is Newton into meter, Newton into meter, okay? Don't write here joule, no doubt Newton into meter is equivalent to joule, but here you please don't write joule, because if you write joule, somebody will be misguided as if it is work done. No, it is not work done, it is right now torque. Though torque and work have same unit, have same dimensional formula, they are basically very different physical quantities. Torque is a vector, work is a scalar, okay? And one more thing, here they have given this electric dipole moment directly in coulomb into meter, but in examination they may give it indirectly this way. They may give magnitude of either charge in a dipole, and they may give distance between two unlike charges. So at that time you must use the formula P equals to 2A into Q, P equals to 2A into Q, correct? Where 2A is the total distance between two unlike charges in a dipole, and Q is the magnitude of either charge. Here value of P is given to you directly, so no problem, correct? Fine. Now in textbook by mistake the illustration number 12 is not given, correct? There is some mistake in the order of numericals. They have simply skipped the example number 12. So let us add one example extra. Come on. What is that example I am showing you? Suppose we are given electric dipole in which this is negative charge, this is positive charge. Okay? Dipole moment vector is always from negative to positive charge this way. So, vector P is like this, correct? And in the same direction of vector P, there is a unit vector P hat. Now, what is the statement in this example? Find out electric field of an electric dipole at its midpoint. That midpoint is this, okay, say point O, where we have to find out resultant electric field. Let us find out. I told you as many charges, that many electric fields. If we have two charges, we should have two electric fields. Come on, let us find out electric field produced by this positive charge at this very point. Let it be vector E positive, correct? Vector equals to magnitude multiplied by unit vector. What is magnitude of electric field produced by point charge? K into charge upon distance square. This distance everybody must have remembered, it is small a, which is half of 2a, correct? Length of the dipole is distance between these two unlike charges, which was 2a, and half of that 2a will be a. So, K into charge upon distance square multiplied by unit vector. For a positive charge, its electric field is away from it. Away from this will be like this. And like this means what? Opposite to P hat. Opposite to P hat. So, I am writing here minus P hat. Similarly, at the same point, what is the electric field produced by negative charge? Let it be vector E negative. Vector equals to magnitude multiplied by unit vector. Magnitude K into charge upon distance square. K into charge, magnitude of minus q is also plus q only, divided by square of distance, square of this distance, that is a square, multiplied by unit vector. Unit vector in this direction is minus of this, because direction of this for a negative charge, don't you know, electric field is pointing towards it. For a negative charge, electric field is pointing towards it, and this direction you can see it is opposite to this. So, opposite to P hat, I am writing here minus P hat, correct? And now tell me, what is the resultant electric field at point O? Let it be vector EO. It should be vector E positive plus vector E negative. Vector E positive plus vector E negative. Come on. These two vectors are in the same direction, correct? So, straight way you can make their addition. Come on. Vector EO as it is, vector E positive, vector E negative. They are in the same direction, having same magnitude also. So, straight way you can make addition this plus this. When you take this plus this, it is 2kq upon a square into minus p hat. So, this is giving you resultant electric field at the midpoint of the dipole. This is bit long method. I am showing you second method, which is very easy. What was the formula for finding electric field due to an electric dipole at any equatorial point? Remember that formula? Vector E as a function of y. It was equal to kp upon y square plus a square whole raised to 3 by 2 into minus p hat. Same formula written here, kp upon y square plus a square whole raised to 3 by 2 into minus p hat, correct? This is the electric field at an equatorial point, which is at distance y from the midpoint of the dipole. But we want electric field exactly at this midpoint, so this distance y is right now 0. That's why instead of y I am putting 0, correct? Come on. When you take y equal to 0 here, come on, put y equal to 0, this part is 0, then a square whole raised to 3 by 2, these powers when you multiply, 2 will cancel, giving you a cube. So, k as it is. What about p, electric dipole moment? It is 2a into q by formula, 2a into q, and as I said 2 will cancel, giving you a cube in the denominator minus p hat in multiplication as it is. And now, this is, come on, 1 is getting cancelled from numerator and denominator. So, now it is 2kq upon a square, 2kq upon a square into minus p hat. You can see these two formulas same, correct? So, this method is rather very easy, you may go for this method, okay? Now, somebody might have question in his mind, the way we are using electric field for equatorial point, can't we use here formula for electric field at some axial point, because this point is also present on this axis? No, we cannot use that formula for finding electric field on the axial point. What was that formula? Vector E as a function of z. What was that? Come on, 2 kpz upon z square minus a square whole square into p hat. Remembered? But that formula you cannot apply here, because while deriving that formula I told you 2 to 3 times that this is the formula for finding electric field at any axial point. That is true, but that axial point must be outside the dipole. Do you find this point outside the dipole? No, it is midpoint of the dipole, so it has to be inside the dipole. That's why that formula you cannot apply here, correct? Whereas this formula you can apply it for any equatorial point, might be inside the dipole, might be outside the dipole. That's why we are applying this formula. Got it? Kindly read this statement of illustration number 13. Read it? Come on. We are given linear charge distribution over a circle of radius small a, and now we are asked to find out what is the total quantity of electric charge contained in that linear charge distribution. The linear charge density in that distribution they have given by formula lambda equals to lambda 0 cos square theta. Fine. Let us find out total charge contained in this linear distribution. Okay. Mind well, my dears, here you don't consider simply a geometrical circle. No, there is a presence of point charges arranged continuously. Fine. Now you just do one thing. You just divide this entire length into extremely small length elements. And one such small length element I have shown here, correct? Its length from here to here I am taking dl. Fine. Now the angle made by this length element, that is arc of this circle, at this center of the circle is I am taking d theta, because it is extremely small angle, and this angle I am taking as theta. Angle made by considered length element with x axis I am taking as theta. Fine. Now what about length of circular arc? It is always radius into angle. Radius is a, angle is d theta. Fine. Now for a linear charge distribution, will you not recall linear charge density formula? Lambda equals to dq upon dl. dq upon dl. This is the charge of charge element, this is length of length element. But what is the formula of lambda right now given to you? Lambda equals to lambda 0 cos square theta. This dq as it is. And what about dl? dl is right now a d theta. dl is a d theta. Correct? Find out dq now. Transfer this. When you transfer this, dq will be a lambda 0 into cos square theta into d theta. Fine. Now just take integration on both the sides. Integration on both the sides. Integration dq. When you take integration here, a lambda 0 is constant, can be taken out of this symbol of integration. Then integration of remaining part, which is cos squared theta d theta. But mind well, why we are taking integration? Because this is going to give you some partial amount of electric charge. We don't want partial amount, we want total charge contained on this entire circle, and for that sake we must take addition of all these partial amounts of electric charges. That's why we are going for integration. But when you take integration, you must take care of that point that you are going to include all these charge elements, and that's why you should integrate this function in such a manner that all these charge elements must be included, and for that you should integrate this function right from minimum value of the variable to the maximum value. When you take this length element over here, minimum value of theta is 0, and when you shift it continuously on this circle and when you bring it here, finally maximum value of theta is 2 pi radian. That's why remember, lower limit of integration is smallest value of variable, which is right now theta equals to 0, and upper limit of integration is maximum value of variable, which is right now 2 pi radian. Correct? That's why I am putting the limits from 0 to 2 pi, 0 to 2 pi. And when you integrate this function from 0 to 2 pi, you are going to include all these charge elements, and then you are making the summation of all those partial amounts of electric charges. Naturally, you will get total charge, let it be capital Q. Okay. Now this A lambda 0 as it is. But what about integration cos square theta d theta from 0 to 2 pi? It is given to you in the hint in the statement, and it is pi. It is pi. So just rearrange it properly. Pi A lambda 0. Pi A lambda 0. Okay. What is lambda 0 here? You can say maximum linear charge density. Why maximum? When you want maximum value of lambda, you may write here lambda maximum. But when you want lambda to be maximum, this cos square theta must be made maximum. What is maximum value for cos function? It is 1. 1 square will be 1. 1 into lambda 0 will be lambda 0. So no doubt the symbol is lambda 0, but it indicates maximum value of linear charge density. Okay. What about A? It is the radius of a given circle. Pi value everybody knows. So they may ask in another way. They may give you these values, and they may ask the total value of electric charge. Okay. So at that time numerical answer you are supposed to find out. Right now there is a formula, but if you remember that formula, you can make use of it. Okay. Fine. Kindly read now statement for illustration number 14. Read it. Look, we are given a straight, extremely thin wire which is made charged, and the total charge contained in this wire is small q, having total length capital L. Correct? When it is placed horizontally like this, we are asked to find out resultant electric field at this point P, which is lying on its axis, such that its position is at distance A from this right end. Okay, fine. At point P, we have to find out resultant electric field. Let us find out. This much length of the wire is L. This much distance they have given a small a. Fine. You just do one thing. You just divide this whole length into extremely small length elements, and one such length element are shown in the diagram here, and the length of that length element I am taking as dx weight. For a linear charge distribution, would you not recall the formula for linear charge density? It is lambda equals to dq upon dl. dq as it is. What about dl? Because this length is aligned along x-axis, I would like to show it by symbol dx. So instead of dl I am putting dx. Transfer this. So find out dq, it will be lambda into dx. dq equals to lambda into dx. dq equals to lambda into dx. Fine. Now the charge contained in this charge element is having such a small quantity, it can be taken almost like a point charge. And due to a point charge at a point at distance x, what is the strength of electric field? Let it be dE. Why symbol dE? Because we are considering partial amount of charge, we should write this symbol for partial electric field. dE means not total electric field, partial electric field, because we are not considering at present total amount of charge, we are considering part of that. Okay, that's why. So let us find out this partial electric field, and due to a point charge, what is the magnitude of electric field? K into charge upon distance square. Come on, K into this charge is dq upon distance square. Distance of this point from this chosen length element is x. It's a square, so I am writing x square. Correct? K into charge upon distance square. And now K as it is. What about dq? dq is lambda into dx. dq is lambda into dx upon x square as it is. Wait. I simply don't want electric field produced at point P due to single charge element. No, I want resultant electric field at point P produced by entire charged wire, and for that sake you must go for taking integration. Come on, take integration on both the sides. Integration of dE, and when you take integration here, look, k into lambda is constant, can be taken out of this symbol of integration, then integration 1 upon x square dx, integration 1 upon x square dx. Wait, just now I told you, whenever you take integration, the lower limit is minimum value of variable and upper limit is maximum value of variable. Right now variable is in terms of x, and minimum value of x will be here for this right end, which is this much, that is small a, and maximum value of x will be for the left end, which will be this much, that is L plus a. Minimum value of x is a, maximum value of x is L plus a. Got it? When you take integration of partial amount of electric field, naturally you will get resultant electric field, that is capital E. K lambda as it is. What about integration 1 upon x square dx? By formula it is minus 1 upon x, minus 1 upon x. Forgotten? Just recall that formula, integration x raised to n dx. What was that? X raised to n plus 1 upon n plus 1. Similarly here, when you take this x square up in the numerator, it will be x raised to minus 2. So integration x raised to minus 2 dx, it is x raised to minus 2 plus 1 upon minus 2 plus 1. That is x raised to minus 1 upon minus 1, that is minus 1 upon x, minus 1 upon x. Wait, lower limit is a, upper limit is L plus a, correct? Should I ask one question here? Why we have taken the scalar addition of these values? Why not vector addition? In fact, the resultant electric field should be obtained out of vector addition. Then instead of vector addition, why we are going for scalar addition here? Reason is very simple. Look, all the charge elements along the length of the wire have positive charges. Whether you take this charge element here or here or here, anywhere, all those charges are positive. And because of positive charge, don't you know direction of electric field is away from it. So away from this will be like this, away from this will be like this, away from this will be like this. So at point P, directions of electric fields produced by all the charge elements will be pointing towards the right hand side right now, that is in the same direction. Because all these partial electric fields are in the same direction, then you can go for scalar addition. That's why I am writing only E and not vector E. Got it? Fine. Now just put up the limits. How would you place the limit? First of all, upper limit. After putting minus sign, you must place the lower limit. Come on, k lambda as it is, correct? Now in this bracketed term, in place of x, you are supposed to write upper limit first. Write it, minus 1 upon x, value of x is L plus a. After putting minus sign, you must write the lower limit, that is in place of x, you must write a. Minus 1 upon, in place of x, when you write a, it is minus 1 upon a, correct? Now tell me, minus minus plus. So that positive term I am writing first, 1 upon a, correct? And minus 1 upon L plus a, I am writing later on, minus 1 upon L plus a. And outside term k lambda as it is. Okay, fine. Now simplify. K lambda as it is, take LCM here. LCM will be a into L plus a. A into L plus a. This L plus a will be multiplied here. This a will be multiplied here. Come on. Plus a minus a will cancel. Now k as it is, whatever lambda, linear charge density, it is total charge upon total length if it is uniform charge distribution, correct? Here there is a uniform charge distribution, then total charge on the entire wire is small q, they are given in the statement, divided by total length of the wire is capital L. Come on, this L as it is upon a into L plus a as it is. Now this L and this L will get cancel, giving you kq upon a into L plus a. Come on, a into L plus a. So this is the required final answer, but we would like to place one note here. Look, what is that note? This axial point lying on the axis of this wire, if you consider very far, then this value of a will be very large as compared to this length. If value of a is very large as compared to length, then mathematically when a is very much greater than L, then in place of L plus a, because a is very large, then L can be safely neglected in addition, and if you neglect L, then this addition is as good as a. Okay, so in place of L plus a, you can write a. write it over here. In place of L plus A, you may simply neglect L and you may write only A. So A into A will be A square, correct? So KQ upon A square, KQ upon A square. So mind well, so far very far axial point is concerned, the total charge contained in a straight charged wire behaves as if it were a single point charge. I repeat, because this is the formula for electric field of a point charge, K into charge upon distance square, correct? So from this you can just express that result in words like this. So far very far axial point is concerned, the total charge contained in the charged straight wire behaves as if it were a single point charge. Okay, fine. Whatever direction of this resultant electric field, very simple. All the partial electric fields are pointing towards the right hand side right now. This point P is on the right side, and because all these directions are in the same direction, and that same direction you can see it is from left to right, that is from point A to point P. From point A to point P, I am writing here from point A to point P. Got it? So we have found out magnitude of electric field, we have found out direction also. Okay.